Alrighty friends, welcome to the last installment of this week's videos, continuing and perhaps finishing talking about waves. So we just talked about how wave depth can influence the energy of the wave and also the speed of the wave, and what factors can create waves and can restore waves and things of that nature. So now I just want to take a little bit to talk a little bit further about some of these things like speed and wave heights and things of that nature. Starting with something called group speed. So waves can travel in groups, which is really quite fascinating. They have like a ripple here, like with this picture over here on the right-hand side, almost as if you like dropped a stone or a rock into a pond or river, and you can see as the ripples move outwards. So the longer wavelengths continue to move out faster than the waves with the shorter wavelengths, and then they end up dispersing. And then the front-running waves disappear, and a new wave appears at the back of the group. So I know it's kind of a lot of words and some things to kind of think through here. So that's what this schematic is attempting to show. So say here at some time we have these four waves, 1, 2, 3, 4. And sometime later, the number one wave disappeared and a new wave appeared at the back. And an even longer time later, wave number 2 disappeared and wave number 6 appeared at the back. So we can see that these four waves have continued to trek forward, but the individual waves themselves have started to kind of fizzle out and disappear. So we have the group advance, which would be where the back of the last wave is. And then we have the individual wave advance. So 4 started back here, and now 4 is all the way up here. But the group has also kind of progressed forward a little bit as well. What's kind of interesting with group speed stuff is more kind of related to the atmosphere, but it's really fascinating when we have these groups of waves in the atmosphere, and as they progress through and bringing energy and things like that through the atmosphere. It's really quite neat, I think. Then there's something called wave interaction. So where we have when two waves come together, if wave 1 and wave 2 come together and their two crests come together, then there's an amplification of that crest. Same thing with the troughs. If two crests and two crests comes together and two troughs come together, then it just really amplifies the size of these waves, which is really fascinating, I think. In a similar vein, they can also cancel each other out. So if a trough of one wave interacts with the crest of another wave, then those two energies cancel out, and you would basically have just flat water. A couple of weeks ago when we had that crazy windstorm here in California, and we looked at some videos of the very, very tumultuous bay, and I tried to really iterate like, hey, listen, look, this is the bay, and we can see wave interaction here. So as the waves were coming and crashing up onto the Embarcadero and refracting backwards or reflecting backwards and interacting with waves that were coming in, we could really beautifully see that gorgeous amplification of those as those two energies collide, basically. And what's also kind of interesting is this process can also create some sort of like checkerboard-like appearance. So these are called square waves. And you can see it kind of in both of these, in like the drawing schematic as well as this actual picture. So the drawing schematic makes it seem like they're always like perfectly square, but in reality, that's not necessarily the case. But I encourage you next time you go out on the water, whether it be, to a lake or a river or the ocean, try to look out for these waves and see if you can spot them with your very own eyes. So wave heights are also determined by three main factors here, one being wind speed. So the faster the wind, the larger the waves. And we've seen this in this year's current weather stuff. As long as we've been paying attention in the current weather discussions, right? But I've tried to really show that when there's windy spaces, the waves can be treacherous. Wind duration. So how long does the wind blow over the water? Is it just like a short little, or is it a sustained wind for a long period of time? If the wind isn't going to blow for very long, then you're probably not going to churn up that much energy. But if the wind is blowing for an elongated period of time, then you're going to be able to have a greater chance at making those waves nice and big. And then the last thing here is fetch. So how far away is the distance over the water that the wind blows in the same direction? So that can be related back to storms as well. So what's the distance of the storm? How large is it? Is it something really small? Is it big? And is it blowing in the same direction? Then there are a couple of waves and terms here that I want to just mention. First being significant wave height. So significant wave height is the average wave height of the highest 1/3 of the waves on a long record of wave heights. I know that's kind of a lot, but basically a significant wave height simply means the highest 1/3 of waves ever. And what we're looking at here on this map is looking at significant wave height in meters with the color scale. The warmer the colors, the higher the waves. The cooler the colors, the shorter the waves. And what's really fascinating here, I think, is we can really see that the Southern Ocean has the greatest significant wave heights. And that makes sense because the Southern Ocean is the most hostile in terms of weather as well as waves. There's a reason why we haven't done a whole lot of research down there because it's hard to stay still because it's very the roughest seas on Earth are in the Southern Oceans. The next little wave I want to talk about are rogue waves. And rogue waves are fascinating because they are individual waves of exceptional height or of abnormal shape that are more than twice the average of the highest 1/3 of all wave heights in the current wave record. Whew, again, a big old bundle of words there. But basically, rogue waves are just insanely tall waves that kind of come out of nowhere. Which is really kind of fascinating. And these waves can sink cargo ships and do sink cargo ships even to this day, which is really quite fascinating. I have a friend in the Navy, who was in the Navy, and it's really fascinating to talk to him about how ships are built and how like cargo ships are actually not really properly built in a way. I mean, they are, but they aren't. So if a rogue wave can take down a cargo ship, just know that rogue waves generally can't take down naval ships. So have no fear there. If you've ever wanted to go into the Navy, you'll be fine. Okay, so beyond that, now we've kind of talked about these sort of deep water waves, if you will, where the wave energy is not interacting with the bottom of the ocean as far as we know. Now I want to talk a bit about shallow water waves. And shallow water waves, the speed of them is determined by the water depth. So the shallower the water, the slower the waves are going to go. And that's what this equation here is trying to show. So the speed is determined by the square root, that's what that is trying to show there, times gravity times depth. So the shallower the depth, the slower you're going to go, which is really kind of fascinating. So that's what this graphic is. I like this graphic a lot because it breaks down this idea really nicely. Notice here how the wavelength decreases and it also gets taller. It's kind of hard to see speed here, but yeah, the wavelength decreases as you have more interaction with the bottom of the ocean. The wave height increases and the speed also slows down. And this is something that's really wild when we start talking about tsunamis. Next thing I want to talk about is as waves approach the shoreline, they do this transitionary period from deep water waves to shallow water waves. And then they start to interact with the land masses around here as well. So it's not just the fact that they start feeling the bottom of the ocean and they slow down and all this stuff, but now they start to interact with land masses here. And we'll talk a little bit further detail later on when we start talking about coastlines and stuff. But I do just at least want to start with this idea of refraction. So refraction, there's a couple of panels here. We'll start in the bottom left. So as the waves interact with the shore, as they're slowing down, maybe the depth of the bottom of the ocean isn't quite level. And so because of that, then the waves are going to start to come up onto land, but not entirely parallel. Yeah, not entirely parallel. They have a little bit of an angle to them, which I think is really fascinating. And then we have a bay indentation. So where the bay is kind of jetted out, the energy is going to be absorbed more so at the tips of those bays, if you will. And underneath, you can kind of see how there's like this little whoop, this little dip here. So that's indicating that the bottom of the ocean has a sort of valley there. Whereas with a headland, which is down here in the bottom right, underwater we would kind of see almost like this underwater hill, and more energy is being felt here at the tip of this headland, which makes sense, right? As the shallower the water gets, the less energy there is, the slower the wave goes, etc. So the further out the headland is, the more energy is being felt at that direct headland. So here's an example of wave refraction on an embayment. So you can see here that like further out where these looks like little rocks are, it's more tumultuous back here than it is in the actual little bay itself, which I think is really fascinating. So I encourage you next time you go to the beach to see if you can find little pieces of these ideas. Then the next interaction is wave reflection. So as a wave comes into the coast, it hits the coast and is reflected back away at the same angle. So that's what this is trying to show here. So as the wave is coming into this little coastline here, it's coming in, and then crashes up to it, and then the energy is then reflected away, but back at the same angle. Or reflected away at the same angle. It's not like it's doing weird topsy-turvy angle sort of situations here. Then the last thing is wave diffraction. So this is caused by the spread of wave energy sideways to the direction of wave travel as it approaches the shore. So something that some communities will put into place in order to kind of get towards erosion, to the issue of erosion, is using breakwaters. So when you put basically like these long lines of, for example, rocks out in the water, then it's absorbing that energy, and then the energy is then diffracted through like these little kind of little breaks here. And so that can sometimes help with the issues of erosion, which is really quite fascinating. But see how the wave rays here are kind of spread out as the energy comes through these two breakwaters, and then sometimes you can even see those square waves that we talked about earlier. Okay, so the last little bit that I want to touch on here is breaking waves. So maybe you've wondered to yourself, how and why do waves break? Well, they end up interacting with the bottom of the ocean, and then mathematically speaking, when the wave steepness is greater than or equal to 1/7, the value of 1/7, then the wave will start to break and kind of crest over, which is really quite fascinating. So sometimes you can go to beaches and waves can be crashing like really far up into shore, or waves can maybe be crashing kind of further away. And maybe on windier days, you've seen more breaking waves further out. And if it's not very windy, then maybe you've only seen them come through just at the coast. Kind of a fun little thing. We'll go into more details of how different types of waves, like there's the coastline affects the way the waves break, and so we'll pick up on those ideas when we return together. So thank you again so much for your time and attention, and I'll see you all in a few days. Thanks.